Okay. Okay. Hi, everyone. Thank you for everybody coming to talking today. You have with talking Juan. Uh, this is a more one colloquium of the Department of Physics of Federal Rural University of Pernambuco. And thank you, Junaid, for this your time to be here and talk you for about your work and introduce better I will call Hermes. Please Hermes, come here.
Okay, hello everyone. It's a pleasure to talk about Junaid because we both were contracted to work here at the University of Leeds at the same time. He as a experimentalist and me as a theorist. And Junaid comes from India, okay, from the University of Hyderabad. I'm sorry, Junaid, for the
It's all right.
pronunciation. Okay, and he has a lot of experience on optical experiments. Okay, doing with liquid crystals. Okay, and today we will hear about his job, his works, his research about it. Okay, so I will pass the word for Junaid, and once more, thank you so much for your time here, Junaid.
Thank you so much. Thank you, Anderson, and thanks, and thanks everyone for being here to attend my talk. So, let me share my screen first. Can anybody see the screen?
Yes.
Is it full now? Is it in full mode?
No.
No, with the
Okay.
same problem before.
Okay. Just now.
Yeah.
Now that's okay.
Perfect. So thank you, Anderson, and thank you, Ernst, for giving me the time to present my work today. So good evening to everyone over there in Brazil. I guess it's evening, if I'm not wrong. So today I'm going to talk about spherical optical microcavities based on liquid crystal droplets. So I am basically, as Ernst mentioned, we are both research fellows back in the University of Leeds. So we both joined together at Leeds University. I'm an experimentalist and Ernst is a theoretician. We work in the same group in soft matter physics. So basically where I come from, just a moment. Yeah. So my origin, I did my PhD from University of Hyderabad back in India. This is the main entrance of our campus. And as the University of Pernambuco, please forgive me for the pronunciation. So you guys are known for porous stones, but in our campus, we have solid stones. That's the difference. So yeah, so basically I have done my PhD from University of Hyderabad. Then I moved to University of Leeds here. And now currently I'm presenting my talk from Leeds back to University of Pernambuco. And it's something like this. So my presentation basically divided into three sections. Initially, I would give a small introduction about whispering gallium optical resonance, lasing action, and liquid crystals. And next, I will follow with my results that I have acquired during my PhD program. And eventually, I will finish with the summary and acknowledgements. So to begin with, so far, solid state based optical microcavities have been studied extensively, and they possess a high quality factor as well as low mode volume. However, the solid cavities, they are very rigid in structure, and as such, they cannot be deformed so easily, and thus they lack the tunability in the whispering gallery modes. And at the same time, their size as the miniaturized dimension is very hard to realize as compared to the liquid crystals. So with this motivation, I started my research on liquid crystal droplets. And so far, many different structures of liquid optical cavities have been studied. For example, bottleneck type structure. This is spherical silica structure. You could see fabric type, disc shape, ring shape, and so on and so forth. So what are the basic attractions of these optical microcavities, they can be used as optical sensors. In the optical sensor, you just confine the light inside the droplet or any optical microcavity, which can be seen in the form of a peak. And then bring any outside material close to this surface. It will reflect in the shifting of peaks. If initially it was here, it will shift here. This way it will display the optical sensing application. And next, they can be used as optical filters as well. In the optical filters, when you confine the light inside an optical microcavity, you bring an optical fiber near to it. This light can go through this way, and at the same time, some of the other lights can just go through and drop in another optical fiber this way. And this way, we can add as well as drop whichever wavelength we want from the optical fiber. And also, since these spherical microcavities, they laze, which we will see in the later part of the talk. So many of the droplets can be coupled together a single optical fiber. This way we will get one laser having multiple wavelengths lasing at the same time. Yeah. So some of the important parameters that are used to define the quality of an optical resonator are quality factor and pre-spectral range. I will try to keep the talk as basic as possible, so as to get the whole audience's attention. So the quality factor is defined as experimentally we define it the resonant wavelength divided by the full width half maximum to that very peak, and it actually signifies the amount of time the light spends inside the droplet inside this optical cavity, and actually signifies how lossy the optical microcavity could be. And the loss is contributed through many contributions. For example, the material loss, which is basically because the absorption and scattering of the material, and then the coupling, where you used an external source to couple the light in and outside of this cavity, which also contributes some loss. And at the same time, surface scattering. It happens in case if there is a surface roughness on the cavity, which results in loss of the light. And also, in case of liquid crystals, there's a special loss associated with the director deformation. By the director deformation, we mean that the liquid crystal molecules, they thermally fluctuate with respect to time as well as with respect to temperature. And also the radiation loss. Radiation loss is very predominant in case of smaller droplets, where the curvature is too smooth as compared to the bigger ones. Hence, the loss is very high in case of smaller droplets. And also the free spectral range. Free spectral range is defined as a spacing between two consecutive peaks in the spectrum, whispering gallery mode spectrum, and is given by this formula, but it shows inverse relation with the radius as well as the refractive index of the material of the resonator. So far, whispering gallery modes have been studied in different structures. Historically, it was Lord Rayleigh who first in 19th century studied whispering gallery modes from acoustic waves in St. Cathedral Church in London, where a talker basically speaks something here and the light resonates around the walls of this very structure and could be seen at higher intensity across these positions. And so he analyzed these acoustic waves and gave the name whispering gallery mode optical resonance. Whisper is the word that derives its roots from sound. Gallery is basically this curved structure, which is also called a gallery, and whispering gallery mode waves. And the waves are basically the waves that interfere inside this dome-like cavity. Similar sort of structures are found across the globe in many parts of the country, in many parts of the world. Especially in India, we have this structure where you could observe the similar phenomena for sound waves. And so with the time, scientists predict that similar phenomena could be observed in case of optical waves. And as you could see here, this optical microcavity where the light is confined right at the interface, and it's circulated within this optical cavity as well as this way. So basically what happens in the optical microcavity? So this whispering gallery mode optical resonance phenomena is based on total internal reflection. When a ray of light is incident from a denser medium to a rarer medium at an angle greater than the critical angle, the light is bounced back to the same medium, and the light reflects internally. And when the light meets, it originates at a single point and it comes back and forth to the same position, it interferes constructed to give rise to the whispering gallery mode waves. To make that happen, the the refractive index of this very cavity has to be higher than the surrounding medium. So, and this is the ray optics, and this is the wave optics, how the whispering gallery mode phenomena occurs within these optical microcavities. And this conditions is observed when the circumference 2 pi r multiplied by the refractive index of the material is an integer multiple of the wavelength. Next. Yeah. So in case of liquid crystal birefringent, which means that they possess two types of refractive indices. So these whispering gallery modes can be categorized into two polarizations, namely transverse electric and transverse magnetic. In case of transverse electric, the electric field of the wave propagating along this droplet is parallel to the surface of the droplet. And in case of transverse magnetic, the electric field vector of the this propagating wave is perpendicular to the longer axis of the molecules. And also, so this is a conventional diagram of a laser where basically two resonators are used. One is highly reflective, having nearly 100% reflectivity, and another is less than 100%. As such, we have a gain medium inside this, which is pumped with external energy, and the gain medium, it emits light. When we pump in sufficient amount of energy, a stage comes where the 2-minute emission occurs, and that light bounces back and forth between these two resonators and eventually comes out in the form of a laser line. So quantum mechanically, what happens, for the sake of simplicity, I'm using this two energy level diagram. So initially the molecules are in the ground state. When we excite them with the external pump source, they absorb light energy and go to the excited energy state. From there, they come down, releasing the photons, and those photons, go back and forth between these two walls and eventually lays out. So to many of you, I'm not sure whether you people are familiar about liquid crystals. So basically, all of us are aware about three states of matter: solid, liquid, and gas. And in case of solid, a crystalline phase. In crystalline phase, the molecules have orientational order as well as positional order, which means they have fixed position as well as orientation. But in case of isotropic phase, like water, so the molecules don't have any positional order, nor do they have orientational order. They are randomly arranged in the space. However, in case of liquid crystals, these molecules, they tend to have a specific order, orientational order, and sometimes positional order as well, which is more or less analogous to a crystalline phase, but at the same time they flow like liquids. That's why the name is liquid crystals. Liquids, some properties of liquids, and crystals, some properties of crystalline phase. That's why we call them liquid crystals. So, and now when we go into the liquid crystal, there are many different varieties of liquid crystal as well. So I don't want to complicate you guys further. So the simplest of liquid crystal phase is nematic phase. In the nematic phase, the liquid crystal molecules are oriented in a particular in one direction. And in case of smectic A phase, we have layer structure. You could see one layer, second layer, third layer, and at the same time, the molecules tend to orient in one direction as well. And when we go to smectic C phase, they have orientational order, and at the same time, this layer structure, and at the same time, these molecules, they orient at a certain angle with respect to the layer normal. So this is smectic C phase. And so in case of liquid crystal, we define director. Director is basically the average direction in which all the molecules tend to orient. And we denote it by this N unit vector. And as I already said, liquid crystal bireference, so we have dielectric anisotropy, where we have epsilon parallel correspond to the longer axes, and we have E perpendicular correspond to the shorter axes of these molecules. And also I have used ferroelectric liquid crystal. So in the ferroelectric liquid crystal, the molecules, they tend to, this is an imaginary cone. If you could see here, the molecules are aligned along the circumference of this cone, and in the next layer, they have made a slight rotation, went there, and the next they keep on rotating like this. And at the same time, they possess spontaneous polarization, which is denoted by this green arrow here. So ultimately what happens over one layer after another layer, this polarization, spontaneous polarization rotates as well. So the elastic deformation in case of liquid crystal is mainly of three types. So these liquid crystal molecules, they can deform into this shape, which terms as splay. You could see this way. And in case of twist, the molecules, they tend to orient in this fashion. And in case of band is simple, they bend like this. And these are the common two types of droplets that are mostly seen when we form liquid crystal droplets in certain polymers. This is basically a radial droplet wherein the molecules are oriented, in this fashion. And in case of this is a bipolar droplet having two defects, plus minus half defects located at diametrically opposite ends of the this droplet. So this is without polarizer image, these two, where you could see two defects, one defect here, one defect here. And these are schematically shown how the orientation of the director is within these droplets. The red lines denote the director here. Some of the liquid crystal compounds that I have used in work are named as 5CB, 8CB, and this pyridine derivative. And the polymers that I have used to suspend these droplets in are basically PDMS, which is highly hydrophobic and non-coplanar, and as well as Cytop. So basically the motivation is you need to have the polymer having a refractiveness lesser than the liquid crystal compound, and at the same time it should be immiscible with liquid crystal so that the droplets sustain in the mixture. And at the same time we wanted homeotropic because of the fact that we want this defect to be at the center, not at these two positions, because otherwise these two positions, they result in the loss of light, which we wanted to avoid. So that's why we want homeotropic anchoring polymer, which forces these liquid crystal molecules to orient perpendicular on the polymer, resulting in a hedgehog defect at the center, but not at the surface. And at the same time, it has to have the low refractive index, and it should be fairly viscous so that the droplets don't move here and there so easily. This is a typical cell which we use to study these spring gallery modes. The yellow portion here denotes the polymer, and these blue balls basically denote the droplets therein. This is a side view of the cell, how it would look like if you look at the side view at the cell. This is how it looks like. So a thin film of polymer having liquid crystal droplets suspended in it looks like this. Under cross-polarized, you could see four brush-type structure. This in a cross-polarized image where you have put one polarizer this way, another this way, and you could see, there is intensity extinction brushes, four intensity extinction, meaning there is no intensity along these axes where the optic axis of analyzer and polarizer lies, which suggests that the optic axis of these droplets at these very positions is either perpendicular or parallel to these polarizer axes, which again signifies that the orientation of the molecules in those droplets is homeotropic in nature. And when we see these droplets without cross-polar, when we remove this cross-polarized, this is how these droplets look like. So basically what we want is that we need to have a droplet having a smooth interface at this position. It should not be rough or having any impurities at there, because this will result again in the loss of light. So this is how a typical droplet looks like in homeotropic configuration. Next. So this is the experiment setup which we have built, and schematically what we need is optical polarizing microscope, which shown here, a high resolution spectrometer to record those string gallery mode spectra, a pulse laser which will be used to pump energy to those droplets here, and a continuous laser sometimes to do some other sorts of experiments. So schematically what we do is we use a laser source here. The light is sent from the back end into this microscope, and from here it is, the dichroic filter reflects it to the objective, and the liquid crystal cell is positioned here. The droplets are here. We focus on a single droplet here with this green light and emits fluorescence there. That light is sent back into this optical path, and from here it goes into the spectrometer, which records the whispering gallery mode spectra. So in order to couple light, basically in order to trap the light inside these optical microcavities, there are generally three methods of doing so. One is direct laser coupling, one is wave coupling, and the last one is fluorescent wave coupling. The direct laser coupling is quite weak in a sense because this does not help in case of liquid crystal droplets because it mostly violates the condition of the critical angle. As such, light is unable to trap inside those droplets. Second method is evanescent wave coupling. This is the most efficient method, but very inconvenient in case of liquid crystals because of the fact that the droplet and this evanescent wave forming optical component has to be within a distance of 1 micrometer, which is very difficult to achieve. That's why for our work we have used the fluorescent wave coupling, where we use an external dye. We mix the external dye with liquid crystals, then we excite that dye inside that droplet to emit fluorescence inside the droplet. That fluorescent light gets trapped inside the droplet, this way resulting in the whispering gallium mode optical resonance in those droplets. So the dyes which I have used are DCM and Nile red. And again, the dye has to be liquid crystal soluble and it should not have any bleaching or very less bleaching. Because of the bleaching, we won't be able to trap light inside those droplets for a longer time. So hence, low or no bleaching is advisable. These are the absorption emission spectra corresponding to these dyes. So basically, we excite these dyes anywhere in this absorption peak, and we get the emission spectra in these peaks anyway. So before I jump into the results, let me give you a small feeling what exactly happens here. Sorry, just a moment. How can I play this? Yeah. So this is a small video. Yeah. So basically what happens now, this is a liquid crystal droplet under cross polarizers. Next, I'm removing these cross polarizers and the droplet looks like this smooth ball. And then this is the laser pointer. This red spot is basically laser. I'm bringing this droplet near to this laser point. The moment the laser hits this dye dope droplet, the dye gets excited and emits light, which could be seen inside this droplet everywhere. So this is how we excite the whispering gallery mode resonance in these droplets. And on the right side, you could see this is a typical whispering gallery mode spectrum arising out of a 10 micrometer droplet. Sorry. So my first work was electrical and thermal tuning of quality factor and pre-spectral range of optical resonance of pneumatic liquid crystal droplets. So in this case, we have used a pneumatic liquid crystal. Before I go into the details, by pneumatic, again, I say that the molecules are oriented in one direction. On an average, they have one orientation order.
Junaid, sorry. The screen is with two. Oh, sorry. You showed two screens. Yeah, you put two. Okay, thank you.
You're welcome. Yeah. So we started forming these 5CB liquid crystal droplets in PDMS polymer. And this is how a thin film of polymer looks like under cross polarized. You could see many droplets are formed across this thin film of different varying sizes, basically. And an isolated liquid crystal droplet looks like this, where different colors suggest the optical retardation, happening from center to the periphery of the droplet. And this is how the schematically these molecules, the rod-shaped molecules, are oriented inside this droplet. And next, we focus on a single droplet and illuminate at its edge. This is the illuminated edge where we focus the laser light at, and these whispering gallium mode resonance are excited and they get circulated within the droplet. So we basically record the whispering gallium mode spectrum corresponding to different temperatures, as can be shown here, 27.5 and 30.5. So these are correspond to the red and black spectrum. And you could easily point out that the shifting has taken place at two different temperatures, which suggests temperature sensing by these droplets. So to study these whispering gallium mode qualitatively, we studied the quality factor corresponding to the highest intensity mode, Quality factor correspond. This is calculated using this lambda divided by delta lambda, while lambda corresponds this very wavelength, and delta lambda is a full width half maximum corresponding to this very intensity mode. And we found that the quality factor decreases as a function of temperature. Why it happens? Because of the fact since we are exciting TM modes are basically depend on extraordinary refractive index in case of liquid crystals, and the extraordinary refractive index is given by this formula, which is having this temperature dependence. When we try to fit this data, the quality factor, with this very relation, we got very close match between these two, which basically suggests that that the loss on account of thermal vibrations is increasing when we increase the temperature. So this way we can actually use these droplets as temperature sensors. Similarly, we studied the effect of electric field on the whispering gallery modes, and we found at different voltage, basically different fields, the shifting of peaks has taken place, which suggests that these small droplets can be used as electric field sensors. And also we again studied the quality factor qualitatively as a function of applied voltage, and we found the quality factor corresponding to the highest mode remains constant up to a certain voltage, and from there it starts decreasing very rapidly. And it draws its similar analogy from Friedrich's transition in case of liquid crystals. What happens in case of liquid crystal droplets? This is a schematic diagram. So the red lines denote director, and these ellipsoids basically are molecules. So what you could see when there is no field, the droplet, the molecules are like this in the droplet. But when you apply the field, the director, basically it tries a line towards the field direction to minimize this electrical energy contribution. So eventually at extreme fields, all of these molecules from here, they orient in the field direction. So this sort of phenomena, this change in structure is supposed to affect the optical properties of the very droplet, because those whispering gallery modes, those are circulating right here at the interface. So any change at these positions will definitely reflect in the change in the whispering gallery mode positions. We also measured the free spectral range of these whispering gallery mode spectra, and we found that the free spectral range increases as a function of voltage as well as temperature. And free spectral range is given by this equation, where it is having a direct dependence on radius of the droplet and refractiveness of the material. When we incorporate these equations into these results which we got, we found there's a discrepancy in both the cases. For example, calculated values using this equation, we should get 0.75, but experimentally we have got 2.09, from 8.5 to 10.5, which is nearly 2.0 nanometer. And similarly, in case of temperature, we should get like 0.15, but we got 2.3 nanometer. So in order to this made us realize that the refractive index is not the lonely factor that's contributing this observation. And next, we tried to measure the radius of the droplets as a function of time as well as temperature. We found that the size of the droplets decreases both with respect to time as well as with respect to temperature. And if we incorporate the rate of this decrease in the size of the droplet, for example, it's 4.5 nanometer for a droplet of this very size, and then calculate this free spectral range, we found that we get nearly 2.0 nanometer free spectral range as a result of this size degradation. So essentially, and similarly, you could see in case of temperature, the free spectral range increases like slowly up to this junction. Then here it changes the slope and goes this way, and which is quite closely reflected in this very diagram, where the droplet diameter as a function of temperature is measured. As you could see, it decreases slowly. Then here it changes shape and decreases rapidly. So in this work, we basically showed that the size degradation as well as the refractive has a close bearing on the free spectral range as well. And in the next part of work, we took this motivation ahead to have a stable system where we don't experience this size degradation in the droplets. So we found droplets in different polymers, for example, PDMS, Cytop, glycerol, and glycerol lecithin mixture. And we found that in case of Cytop, the molecule, in case of CyTOF, the liquid crystal droplets, they tend to have stable size beyond 3 hours of formation. So basically, when we form droplets in CyTOF, so after nearly over 3 hours of formation, the droplets tend to have stable size. And these are some of the results which we saw droplet size in PDMS, where you could see the droplet size degrades very fast. And same is the case in case of glycerol lecithin, although slower in pace as compared to PDMS. To again confirm the stability in case of CyTOF, we measured the free spectral range, and we found that the free spectral range remains constant for longer time. So this which means that there's no change in the refractive index because we are not changing any temperature or any field, and so there is no change in radius as well. And also, we measured the free spectral range corresponding to different size of the droplets, and we found that the free spectral range is quite higher in case of smaller droplets, and it decreases as a function of radius. And this is a close, this fit equation corresponds to this A by D, where the D is the diameter of the droplet, is a constant. In the next part of the work, we study whispering gallery mode lasing in mesomorphic liquid crystal microdroplets. So by mesomorphic, we mean to say a liquid crystal compound that exhibits more than one type of liquid crystal phases. So basically, here you could see the cinematic phase. Then we have smectic A phase, where we have layer structure as well as the oriented order we have, and we have smectic C phase, where we have tilted structure of these smectic layers. Yeah. So here I show these three pictures correspond to three phases of this very compound. This is the nematic phase liquid crystal droplet, and this is smectic A phase liquid crystal droplet. This is smectic C phase. So as you could see clearly in these all these droplets, there's 4 intensity extinction brushes are present, which means that the molecules are radially oriented inside this droplet. And same is the case of in case smectic A as well as smectic C phase. But one could observe that the tilting of brush is taking place in the smectic C phase, which should essentially take place because of the fact that in case of nematic droplet, the molecules are aligned radially in this direction. These yellow molecules denote the dye molecules. And here, in case of smectic A phase, you have smectic layers. Sorry, it's working slowly. Yeah. So these concentric red circles basically denote the layers of this smectic A structure. And in case of smectic C phase, you have layered structure, but at the same time, the molecules tend to tilt with respect to the direct layer normal. So that is what is basically the reason behind this tilting of brush in case of smectic C phase. We also measured this brush tilt as a function of temperature, and we found that the tilt angle, it decreases as we go, as we increase the temperature towards the smectic A phase. And we also measured the bireactions of this very liquid crystal compound to figure out its phase transitions. And this is the bireactions data corresponding to the liquid crystal compound that we have used. And it basically is having 3 these liquid crystalline phases: smectic C, smectic A, and nematic. So isotropic nematic is first order transition. Nematic to smectic is also first order transition, and smectic A and smectic is weakly second order transition. Next, we excite these these liquid crystal droplets correspond to 3 different phases, and this shows illuminated edge corresponding to 1 droplet, and this the whole droplet corresponding to nematic phase. And similarly, these are the smectic and smectic C phase droplets. One could see clearly that the contrast in this very case is quite poorer than in case of smectic A, and is the poorest in case of smectic C phase, which essentially means that we have more scattering loss in smectic C phase, and then next in nematic phase, and the least in smectic A phase. And these are the 3 corresponding spectra, lasing spectra, above lasing spectra, corresponding to these 3 droplets. And the size is 21 micron, 22 micron, and 22 point, which is quite comparable to each other. So these peaks are quite narrow, which gives a hint that these whispering gallery modes are lasing. To study the lasing, whether they have lased or not, we did some qualitative analysis of intensity and light width as a function of pumping energy. What we found that the lasing intensity corresponded to like specific peaks. For example, 616.4 nanometer in case of pneumatic droplet. The intensity increases slowly up to certain pumping energy, and beyond this pumping energy, it changes its slope and increases rapidly. Same is the case, I mean, similar sort of trend is observed in case of smectic A droplet as well as smectic C phase. And at the same time, the line width corresponding to 616.4 nanometer shows increase. I mean, this line width basically decrease as a function of pumping energy and changes slope at right at this pumping energy, and then remains almost constant. So what actually is happening optically is the dye molecules are spontaneously emitting in this regime. At this point, the spontaneous emission, is overpowered by stimulated emission, and at thus the stimulated emission takes place, and the optical losses are lesser as compared to the spontaneous emission, and thus we get lasing peaks in the form of very sharp peaks, as you could see in the previous diagram. These peaks are observed. And also one more peculiar thing here we could see is, for example, at fixed 80 nanojoule, somewhere near here, if you compare the intensities in these three phases, you would see that in case of smectic A phase, the intensity is nearly 5 times, like nearly 55 here somewhere, is nearly 5 times than that is observed in pneumatic phase as well as smectic C phase. We also measured the lasing threshold as a function of droplet diameter, and we found that the lasing threshold, that the cost of this lasing threshold is quite higher in case of smaller droplets as compared to the bigger droplets. And also comparatively, we studied this threshold in these three phases, and we found in case of smectic A phase, on an average, the lasing threshold is lesser than pneumatic phase as well as smectic C phase. And also we've studied this intensity as a function of tilt angle, which we have seen in this very diagram. Just a moment here, sorry. This tilting, we found what's the effect of this tilting on the intensity of these peaks that's occurring in smectic C phase, and we found that the intensity decreases as a function of tilt angle. So that means as we go towards this crystalline phase, the droplet, the intensity of those whispering gallery mode peaks decreases very rapidly. Next, we also studied this whispering gallery mode optical resonance and lasing in case of ferroelectric liquid crystal droplets. By ferroelectric liquids, I would say this is how the ferroelectric liquid crystal molecules look like. So they are arranged around a cone, which is here. So in the next layer, you would see it keeps on rotating. It keeps on rotating. I mean, this is how it looks. So this sort of liquid crystals are very useful because of their low voltage operability, and they show very fast electro-optical response because they have got spontaneous polarization. So these are ferroelectric liquid crystal droplets formed in CyTop, and we see that the structure of these droplets is a function of size. As like initially we have a radial droplet, I mean up to like 5.4, then this radial structure, it evolves into a different structure having a different loop-like structure, and which eventually becomes a hairpin type structure. It so happens because of the elastic deformation that occurs as we increase the size of the droplet. Next. So a typical radial ferroelectric liquid crystal droplet looks like this, where the molecules are again aligned around the circumference of a cone, and in successive layers you could see these molecules, they tend rotate around the cone, and this way they align in this in a radial droplet. So next we choose an isolated liquid crystal droplet, and we illuminate it with the pumping source, which is here is basically pulse laser. And this is a very weakly illuminated speckle here, and the corresponding spectrum looks like this, where we could see clearly very wide peaks and very low intensity as well. And when we keep on increasing this pumping energy, we find that the speckle gets in a strong contrast, which actually shows coherent emission here, and the light is trapped in a very strongly, and this results in the increase of an intensity in these peaks, which suggests that this could be because of lasing action that's taking place inside these droplets. To confirm the lasing action, we again measured the intensity and line width corresponding to the to one of those peaks, like 634.5 nanometer, and we found that they obey this typical two-slope curve of lasing action, where the transition from spontaneous emission to stimulated emission occurs in these droplets. And similarly, initially the line width corresponding to those modes is quite wider, which then narrows up and remains constant, which is basically a lasing peak in this region. Next, we applied electric field to these droplets and to see if there's any response to the electric field, which was quite like expected to happen. And this is when there's no field, the droplet looks like this. And when we increase the field, the change in texture implies that the molecules start to orient towards the field direction. And while doing so, they are basically breaking that helical fashion of their orientation. So we expected this sort of phenomena, this the textural change occurring in these droplets, to impact on the whispering gallery mode spectra, which was rightly observed. This is the whispering gallery mode spectra, lasing spectra, basically corresponded to a 20.1 micrometer droplet size. Initially, we have a nice lasing peak here. These are lasing peaks. Then we increase this electric field, and we found that the lasing intensity started dropping down. And as you could see, it keeps on decreasing and eventually switches off near this field value. And we again measured this lasing intensity and line width of this very line, and we found that this intensity follows again the similar pattern, wherein this lasing intensity decreases rapidly and it changes slope right here. And in this region, we only see these whispering gallery modes up to certain field value, and beyond this value, they eventually switch off. We don't see any spectra. And if we switch off this field value, we again get back this whispering gallery mode lasing spectra, which basically signifies electrically switchable lasing in these ferroelectric liquid crystal droplets. And also we found that the line width corresponding to this very peak, it increases linearly, which suggests that the losses are increasing in these optical resonance on account of field-induced distortion. So this way we demonstrated the electric field, the electrically switchable lasing in these liquid crystal droplets. Yeah. So in summary, we showed electrical thermal tuning of quality factor and pre-spectral range of optical resonance in pneumatic liquid crystal droplets. Also, we addressed the size instability of liquid crystal droplets, and we found CyTOF as one of the best mediums for having stable optical microresonators. And also, we performed first studies on whispering gallery mode lasing in a mesomorphic liquid crystal droplet having 3 liquid crystalline phases. And we compared those lasing actions in those 3 phases as well. And finally, we also demonstrated electrically switchable whispering gallery mode lasing from parallel liquid crystal droplets as well. So finally, I would like to express my thanks to my research advisor, Professor Surajit Dhara, and this our collaborator back in Slovenia, Professor Igor Mezovic, and my doctoral committee member, Bivia Tata. And also special thanks to the funding agencies. And this is my University of Hyderabad, and this is the funding agency UGC and DST Serve for providing me a genuine fellowship during my PhD program. Last but not the least, thank you all back in Brazil for being so patient to my presentation, and I'm open to the questions. Thank you so much.
Thank you, Junaid. Yeah, nice talking. Thank you so much for your time here. And before to start to questions, I want to everyone open the microphones and make applause for the talker. Yeah, thank you, please.
Okay.
Yeah. want to say thank you for you and your nice talking. And now the question is open. Who want to make a question, please? Hermes, someone, Sampaio, Moraes. I started with the first one that handed up the hand. In my list, who up the hand first, the more fast there for Hermes. Hermes, please. After that, I will call Fernando.
Okay. Thanks, Anderson, and thank you, Junaid, again. Junaid, could you explain to me again the definition of the free spectral range?
Yeah, sure.
That you use it, I think, to measure the quality of the whispering gallery modes.
Yeah, could you see the slide here? Could you see the slide here?
Yeah.
So basically, you have seen the spectra, in the following slides, but the free spectral range is basically. Just a moment. Let me get the pointer here. So the free spectral range is basically the spacing between these two consecutive peaks, any two peaks you choose on the spectrum. So the space, the distance from this very peak to this very distance is termed as free spectral range.
Mm-hmm.
Yeah, and it depends on, as you see here, it depends on radius of the droplet as well as the refractive index of the optical microcavity. So I can show you another example here. Just a moment. Here, you choose any two peaks. The distance between. Sorry, here. Oops. Yeah. So you could see this spectrum here, right? Mm-hmm. In this spectrum, the distance between any two peaks is termed as free spectral range. That's called free spectral range. Is that clear now?
Yeah, it is. Thank you. Fernando, I think it's your turn.
Yeah, Fernando, my microphone is closed. Sorry.
Oh, okay.
Fernando.
That was a very interesting talk tonight. Thanks. I took a few notes here, but I won't take too much time. It's very basic questions. Just I wonder, for example, when you studied the temperature variation, if you went up to the nematic to isotropic transition.
Uh-huh.
Yeah, there. Okay.
Okay.
Because I see as temperature goes up, the peaks decrease in size.
Yeah.
But the background stays there, this broad background.
Yeah.
So I wonder if you get very close to the the nematic to isotropic transition, the peaks will disappear. Or...
yeah, like ideally they should not be present, but yes, they are there. But the peaks are. I mean, when we reach to this isotropic phase, basically what happens? The basic condition of total interreflection fails because we no more have the denser medium and rarer medium. I mean, just a moment. I would like to make you understand. Where is that? In just a moment. So, yeah, for example, if you see here, so the refractiveness of this material has to be higher than the surrounding medium. So when we go to the nematic to isotropic phase, this refractive index contrast, sorry, I'm not sure whether you could see here. Yeah. So for this whispering gallery mode optical resonance to occur, those peaks to occur, this condition of having this refractiveness higher than the surrounding medium has to be obeyed. But when we go to this isotropic nematic phase temperature or nematic near to this transition, what we observe is loss of refractive index. And this loss of refractive index contrast results in the peaks nearly vanish. So we no more see those peaks. However, we definitely see those peaks, but very weakly, like intense, in case of bigger droplets.
Oh, I see. So you don't lose the resonance completely.
Yeah, exactly. Yeah, we lose it. Yeah.
Yeah. Okay. Second question is about the electric field that you study also.
Okay.
Because you went a bit fast there. Yeah.
Yeah.
Is the third figure on the right?
Yeah, this one.
Something like the bipolar configuration.
Yeah, exactly. Yeah.
So you get it from the application of electric field. So just by applying a field, you can change from radial to bipolar. Is that?
Well, this is a this is a theoretical paper by Larentovich, where they have shown that this sort of transition is possible in these droplets. However, to be honest, we have not seen this sort of transformation takes place from a radial point effect to bipolar droplet at infinite field. We have not seen that, but this is what theory says that it should take place.
Okay. Yeah, I guess this bipolar configuration is not useful for your studies.
Yeah, as you say, yeah, sure.
Yeah, you need more symmetry for that. And my last question is about this Medic C case that you have there. Yeah, for the droplet. So you have a figure with the droplet. Yeah. I was wondering how would be the 3D structure of this F, the figure F, the last one, because you can just rotate this. Right? If you use the vertical axis and rotate this around this axis, it won't match.
Yeah, exactly.
On rotation, it won't match. So, what happens in 3D? How do you cover the sphere with the bent molecules?
Yeah, you're absolutely right. Like this schematic diagram is not the actual, representation of how the schematic C phase looks like in 3D phase, but this shows just a cross section, a slice of cross section of this 3D phase, how the molecules would be looking like. But you are right that the elastic deformation occurring in schematic C phase particularly is quite complex to figure out. You're right.
Yeah, I imagine there's topological defects that should appear because of this. That's when it happened when the bipolar case, right? You have two topological defects appearing, and you probably have something like that here too.
Yeah,
that's my guess. Okay, thank you, and congratulations for the nice talk.
You're welcome.
Any more questions? One. And thank you. I say thank you, Johan. Thank you for your talk. Nice talking for today. And thank you for everyone to come to watch the talking. And see you everyone next weekend. And nice talking, Juan. See you and bye bye. See you next weekend. Thank you.